So let's move to the new indicator. It's SDG on life below water, and Dimitri with Thomas, they developed the two services, one on water acidification and the other one on eutrophication. So that's the floor is yours, Dimitri. Do you need help, I think?
I'm also new to the I think it was even opened already. I just cannot switch. No, it's a video, but yes, this one, I think.
Is this one?
Yeah, it's this presentation, just from the first slide. Thank you so much. Sorry about this. Okay, sorry about this. Good afternoon, everyone. As Manuel already introduced me, I will be talking about services number 4 and 5 on behalf of Thomas and myself. These services are devoted to sea surface acidity and marine waters eutrophication. Thank you. Okay, good. Yeah. First of all, just to briefly remind you about these indicators. And these two indicators are included into the Sustainable Development Goal number 14, life below water, and have both United Nations and Eurostat numbers in classification. So these two services are devoted to these two indicators, each for one of them. And marine water acidity provides explicit spatial representation of seawater acidity at the best available time scales, which means that we were trying to improve timeliness, coverage, and accessibility. And marine waters affected by eutrophication, it's devoted completely to detection of eutrophication through the application of indicators or marine regions, also with the aim to improve timeliness, coverage, and accessibility. The region of study was chosen, the North Sea was chosen as the region of study because it still experiences eutrophication conditions, and also it's rather complex marine body which has different activities also in terms of well, human activities and yeah, biological conditions. So yes, so as I was saying, it's a naturally nutrient-rich water, and the basin supports a healthy, productive ecosystem, but it's also exposed to severe eutrophication events. And also numerous anthropogenic activities sum up with the pressures of climatic changes posing diverse threats to this ecosystem. So that's why we, in this project, we were trying to achieve and provide an automated system based on Copernicus marine data to increase spatial temporal accessibility of indicators and make it portable to different marine regions. So this is the core team, Tomás Lovato and myself, and of course we wouldn't do it without all of the help of the partners included in our consortium. So thank you everyone. And yeah, so basically a lot of words have been told about the service structure already, but I will just briefly conclude this, that we have the three main parts of the service, which is basically the data storage service, which is organized in the platform, the workflow, automated processing workflow, which is basically the core code which computes all the indicators. And finally, last but not least, it's the indicator discover and visualization system, which basically is the user interface where we can visually see all the results computed. Just a couple of words about the methodology. So for the service 4, we use reanalysis data. Also, within this project, we had a new product, which is like a blended data based on the already available reanalysis data and also in situ data in the North Sea. And also, we even made it possible to include new data sets by end users. of course, given that the necessary requirements such as metadata and like a special domain is maintained. So yeah, now I will continue to the eutrophication part, which is also includes the reanalysis and satellite data, but also can be adapted by to the new data sets. And here I will maybe briefly also introduce the methodology itself, because along with the main indicator of eutrophication, which was already provided by Eurostat, which is based on the percentile values of chlorophyll concentration, we also introduced within our workflow the so-called 𝗏 index, which is also based on chlorophyll values, but in a different way. It takes into account the trend values and also the mean absolute values of chlorophyll concentration. And as a result, we get the map of this 𝗏 index, which consists of 6 classes of water types. I will later show you the examples. So again, as it was mentioned many times today, in this project we used a co-design approach, which is based on the feedback from end users, and we had several cycles along the timeline of the project, and from the users webinar and uptake webinars, we used the information from the end users to improve our service, to further provide more information on the studied parameters. So continue with the demonstration part. First, I will just briefly describe you the main results that we get from the workflow. With the sea water acidification, we have first of all the difference in pH values, and also as an alternative representation of acidity, the hydrogen ion concentration. So here you can see the maps of example maps of these results, and for example, we have the possibility to monitor the changes in marine acidity, not only in certain points or having average values, but also in a special representation. Sorry. So along with the absolute difference values, we also introduced into our workflow the median, the trend values, the maps of linear trend, which shows us the intensity of changes. So, for example, as you can see here, with the difference between 2 decades, we can see that in some regions the trends are increased, but in some regions they even decreased slightly. So it gives us more informative picture of the ongoing process of acidification. So continuing with the eutrophication, we have one of the results is, as I already mentioned, the Eurostat eutrophication index, which shows us the areas in colors of waters potentially affected by eutrophication or oligotrophication. And for example, we can see that some stable patterns are evident. And also we have more than 100,000 of square kilometers of eutrophication area within the North Sea. And this is the example of output for the 𝗏 index of eutrophication, which I already mentioned before. So as I said before, it takes into account the sign of the chlorophyll trend and also the typical absolute values of chlorophyll. Of course, we calculated for each pixel. So as an output, we get these special maps, and we can see rather quite good similarity with the previous slide, but still in a different way, especially along the coastal regions. So, well, as all other pilots, we have two ways of output. First one is a graphical user interface for end users who are not very experienced with the Python language, with the programming, with coding, and also the backend platform where more advanced users in terms of programming, they can even use their own data sets, adapt the workflow, and change the notebooks. So now I will hopefully run the video of the user interface. I should be careful. Yeah, I think so. Yeah. So this is the user interface of our two indicators, acidification and eutrophication, which corresponds to each respective service. And as an input data, we can select several options. First of all, the data type, which is reanalysis or a blended data, year of interest, also reference year. Also select the type of difference between monthly and yearly difference in, and also the parameter, which I mentioned before. And then we click calculate and see the map, and also with the possibility to switch between exclusive economic zones where the mean value is calculated already. So we can, and also we can see the point-wise difference as well. So continuing with the eutrophication, we also have the choice of two different indicators. For Eurostat indicator, we choose the year of interest, also the type of input data. And here we can see the resultant map, which with also the possibility to see the areas within each exclusive economic zone. And as for NEAT index, we choose the period of interest, and then we choose the data type. And here we can see the 6 classes with also areas for each class within each exclusive economic zone. Now I will try to go back. Okay. So concluding with the challenges, of course there are still some potential challenges which can appear from time to time. First of all, the robustness is still might be affected by the input data quality. So we always depend on the data that we use. The replicability, so we provided the workflow, and we use CMEMS input data as a main data source, and it can be used for different other regions. So we can more or less confidently say that we can use this workflow for all the European regions, for example. And also, of course, the guidelines were provided with the documentation to this workflow. And of course, one of the challenges might lie in the fact that the workflow depends on the data publication. So the timeliness might depend on the publication of the actual input data within the Copernicus marine system. So regarding the exploitation and sustainability, the key results, of course, are the codes themselves, the dashboard, which is basically the user interface that I just recently showed you. We have flexible workflow to support user-defined application for marine services, and as well we provided the guidelines for usage of all this tool set. And as a potential uptakers, there can be marine environmental authorities, research institutes, regional sea conventions, and fishermen's departments, and some other agencies. So I'm finished. If there are any questions.
Thank you very much. And there is a question from Claire.
Yeah, thank you very much, Dimitri. Very interesting. I remember there was a lot of interest for these services. I don't know if you remember, in one of the webinars, there was a country expressing interest completely outside Europe. I'm not sure, it was Indonesia or one of those countries. Yeah. they were interested. So suppose you have a country who's interested, how could you help them to get started? Would it be a matter of handing over the code and the guidelines, or how easy would it be to for them to pick up this service?
Of course, the main dependence here lies in the data itself. So if they have already the data that can be used in the same way that we use the Copernicus data, for example, then I don't see any big issues that can arise here. So the workflow is designed in a way that it can be adapted, and if of course the data should be constructed in this certain way. I mean, with a given the metadata, the spatial domain, and so on. But in general, it's I don't see any things that prevent people from using it around the world. But yeah.
Thank you, Dimitri. Just one thing for curiosity. So eutrophication, it's also eutrophication. It's also affecting inland water, not only coast. My question, if you have same data on chlorophyll, I don't know, from Sentinel, to covering a lake, would it be possible to replicate this methodology for a lake, or which is the most constraining, I don't know, part of the methodology that cannot be replicated?
Well, I would say that in general, again, in theory, there are no restrictions here, but of course, lakes are much more complex in terms of biogeochemistry, and they have much more influence from different sources like rivers and so on. But I mean, in general, as a basic approach, of course, it could be used even in lakes, I think. But with the further investigation of the results, of course, because of course it was designed first of all for the bigger marine bodies, yeah, but no restrictions.
Thank you very much.